This little video is truly going to be little, and that's because I'm just looking at energy in the inductor. Now, when I determined the curves for the charging and discharging of the inductor, I came up with some Kirchhoff's equations for the little circuits that we were using. And if we use these Kirchhoff equations, what we find is that we can look at the whole energy of the situation. So we end up with energy supplied by a battery equaling energy lost in the resistor. So I should draw the circuit, shouldn't I? So what we're saying is we've got this resistor, it could be a lamp if you like, and we've got this inductor. And so the energy supplied to the circuit is going to be energy used by the resistor and energy used or stored by the, or energy stored by that. From a power point of view, and I won't prove this, but the power from the battery is just I times E, right? It's just volts times amps. The power in the resistor is I squared R, and the power in the inductor is just going to be Li di dt. That's saying that the power is equal to the inductor times the current times the rate of change of the current. So when the actual inductor stops producing a voltage, which is when di dt equals 0, then that whole power is going to be 0. There will still be a little bit from the natural resistance, but we just include that in the resistance of the resistor. But anyway, if we know that that's actually the power expression, and I won't say how we know that, but we end up with an expression that basically says that the power, well, not the power, but the energy in the inductor is equal to L I squared over 2. And that is easy to use. We've got the inductance of the coil in henries, we've got the current squared, and this is, what are we talking about here? Because we all know that the current has built up to a maximum. Right? Remember, the current builds up slowly. That's our current time graph. And so what we're basically saying is when that current has built up to its maximum point, the actual energy in the inductor, that's the energy in the field. So this is magnetic energy, is going to be equal to half this maximum current squared times the inductance. Sort of makes sense, doesn't it? That's the energy in that field. All right. When it was being charged, there was energy being expended in the resistance also. All right. The voltage on this, remember, was changing throughout the whole process. But at your level, you don't have to sort of understand all the ins and outs. What you do need to understand is the formula.